I don't know how it will behave. Let us see. Okay, so let's start from where we left yesterday. So we are trying to have the model for our symmetrical machine where we see that the equivalent circuit can be drawn like this. So we have to be careful in which reference frame we are referring to. If let us say we refer to stator reference frame, then we will have Vs and Is as it is, which means they are referred in their native reference frame, whereas Vr will be referred to stator and IR will also be referred to stator. So other quantities remain same because we are talking about 1:1 ratio of the winding. So all other quantities remain same. Now similar thing we can draw for the rotor reference frame also. We are drawing two circuits because we are dealing with two equations. One is the stator equation, KVL equation, and another is the rotor equation. So here we will have Vs and Is referred to the rotor reference frame. Whereas IR and VR, this remains as it is. Now we have written the equation also. So let me quickly write that. We have Vs, and this I am writing as general for all three phases. So that's why any subscript I you can take where I would be X, Y, Z or R, Y, B. Fine, which means I am writing the per phase equation for this circuit, which is applicable for all three phases without any problem. So here I have ISI times of RS plus LLS ddt of ISI LM. Now here we have both the currents coming over there. So IS, you may write I plus IR, which is also I. This means that RYZ, any phase we are referring to. Then we can write the rotor equation. This point is clear, right? This is a pretty simple thing what we have seen yesterday. Right? There is no problem in this, no? So we can take out this ISI here and this IRI here. So the combination of magnetizing inductance plus leakage inductance, that can be called as total inductance. So if we talk about the total inductance of a stator, this will be LM plus LLS. And whereas total inductance of rotor, that can be called as LM plus LLR. Leakage plus magnetizing. This is the total self-inductance we can say for the particular winding. So now we can simplify this as I am dropping the subscript I, so it is easier to understand. LS, because this becomes LM plus LLS ddt of IS plus LM times of ddt of IR in stator reference frame, whereas here it becomes IR RR plus LR ddt of IR plus LM ddt of IS in rotor reference frame. Now, since we have three equations, so this is for applicable for all three phases R, Y, B. This is also applicable for all three phases. So I can write the combined equation for all three phases, which means I can write the stator vector. So stator vector, we have seen that it is written as Vsr plus Vsy e raised to the power j 2 pi by 3 plus Vsb e raised to the power j 4 pi by 3. Similarly, Vr vector also we can write Vrr plus Vry plus Vrb. Fine, right? So in a compact manner, all the quantities will be grouped together. So this all, whatever is written individually as per phase quantity, this all will become like a vector because everything we are adding in the same fashion. So what the equation would look like from here, what we will have, this Vs vector will be equal to Is vector times of Rs plus Ls times of ddt of Is vector plus Lm ddt of Ir vector referred to stator reference frame. Similarly, we will have Vr vector. So this is combined form of all three phases. That's what we have been trying to do. Visualize the quantities as vector. This becomes Lr and Ir. Fine. So we have the clarity, right? What is the reference frame for this equation?
Stator.
The first equation is the stator reference frame. And the second equation?
Rotor.
Rotor reference frame. Correct. This clarity we have. Now, see, we can measure what is Is, what is Ir. We can measure this, but we still don't know what is the meaning of this referred to some other reference frame. What is meaning of this? That's what we need to understand. So what we have done basically, and when we are saying vector, of course, we can have only two components instead of three. One which is real, another which is imaginary. So say alpha or beta. So when I am saying my current Is, this vector when I am referring to, this has two components. One which is along the alpha axis or the real axis, and beta which is along the imaginary axis. So this can be called as Is alpha, this can be called as Is beta. Now we have rotor which is rotating at say speed omega r. So when we are talking about the alpha beta reference frame, this is stationary reference frame. But stationary with respect to what? Stationary with respect to the stator. You understand the point?
Yes, sir.
Yes, sir.
Okay. So to differentiate that, this we are talking about the stationary reference frame of the stator, we will have small superscript say S, alpha S, beta S. Because when rotor is rotating, it will have its own alpha beta, which will be stationary with respect to the rotor. So which means this alpha beta will be rotating with omega r along with the rotor. Correct? So to differentiate, I will call this alpha r and beta r. So if I take different color to mark this, say, oh, this is drawing arrow everywhere automatically. Okay, I think. So say this is your reference frame alpha or beta r, which is attached to the rotor, which means this is stationary but with respect to only rotor. What is meaning of stationary with respect to rotor? Which means with respect to stator, it will be going at speed omega r. So if this is making some angle, say epsilon, then d epsilon by dt, which means rate of change of this angle, is nothing but omega r. Correct? Keep in mind this thing. So now what is meaning of this quantity which is Is refer to the rotor reference frame is that we are trying to get how this rotor reference frame is seeing this quantity, which means projections of this vector on these axes, the alpha r and beta r. It is the same vector. When you say is, I am writing is alpha plus j is beta. Or to clarify, small s you can add over here. Now when you say the vector is referred to, say, rotor reference frame R, the projections will be this. This is the projection on alpha R axis. So let me call this as is alpha R. So these are the components of this vector now, is beta R, where is beta R is this. Now it is obvious that we cannot say that is simply equal to isr. Is alpha, or simply if I have to write is not equal to is refer to the reference frame. This is not equal, although it is the same vector, but this is not equal. What does it mean? If you say that this is equal, which means we will be saying that real components are equal, which means is alpha s is equal to is alpha r, and imaginary components are equal. Is beta s is equal to is beta r. Is it equal? No, right? Or is it equal?
Not equal, sir.
So this is not equal, which means that this is also applicable to the vector. Although it is the same vector, we are seeing only from two different reference frames. But this does not mean that these two things are same. You understand my point? Simple understanding you can have. Let us say somebody is sitting on a train and moving with velocity v, right? So you will say that velocity vector is v with respect to what? When you are standing on the ground. With respect to earth only, you will say that the velocity vector is v. But if you go and sit on some other train or maybe on the same train, this vector will change, although we are talking about the same quantity. You understand my point?
Yes, sir.
Correct? This is the similar phenomena what we are observing over here. The vector is same, but we are looking it from a different reference frame. This vector is rotating, is rotating, but with respect to alpha s, beta s, with speed say omega s, synchronous speed. Now you have another reference frame which is rotating with omega r, then this speed will not look like omega s. This will be difference of the two, omega s minus omega r, which is why these projections also must be different. What we are seeing on stator alpha beta axis and what we are seeing on rotor alpha beta axis. So our objective is now to obtain, if this is not equal, then what is this? You understand my point? So this is what we try to do over here. Now, the simple way to obtain this is alpha r, simple way to obtain that is you take alpha is r and express that in terms of the components on the stator alpha beta axis. So what are the components? Is alpha s and is beta s. These are the components on the alpha s beta s axis. You express this component in terms of these two. So what can be done? Which means that projection of this is alpha s and is beta s on the axis alpha r. You understand this geometry?
Yes, sir.
Correct? So now this angle we know that this angle is epsilon. So what will be this component for IS alpha S? This is perpendicular, right?
Yes, sir. Cos epsilon. I alpha cos epsilon.
IS alpha S cos epsilon. And plus we have projection from the beta also. So what is that?
Sin epsilon. As ds sin epsilon.
Similarly, we can write IS beta R. What is that? So beta axis also you may extend on the negative side also. So this will basically come on the negative side. Now what is the component along that beta R?
Minus sin epsilon.
Yes. So minus IS alpha S sin epsilon plus IS beta S cos epsilon. You understand this point completely or any confusion? You understand this point, right?
Yes, sir.
Yes, sir. Yes, sir.
So I can write this in a compact form, these two equations in form of matrix. Let us say I write IS alpha R, IS beta R. This vector I am trying to express in terms of IS alpha S and IS beta S. So I can use or I can multiply this matrix with the vector IS alpha S, IS beta S. You understand this point?
Yes, sir.
Okay. If you write this in terms of real and imaginary components, what you will find is that finally it will come down to IS alpha R plus J IS beta R is equal to product of IS alpha S plus J IS beta S times of cos epsilon minus J sin epsilon. This is the expression of these two equations in vector form. Can you see that? So IS alpha will get multiplied to cos and sin both. So if you segregate the real and imaginary components on both the sides, you will find the same equation again. Okay. Now, what is this vector? This is basically my IS referred to the rotor reference frame. Correct? In the compact form, we are writing that, right? You understand this?
Yes, sir.
And what is this vector? This is my IS vector in the native reference frame. And what is this? This is basically a unit vector which can be written as e raised to the power minus j epsilon. So what has happened? We know the vector in one reference frame. This is, let us say, we know the vector in this alpha s beta s reference frame. We are trying to compute the vector in alpha r beta r reference frame. So we can simply multiply a unit vector with the original vector to obtain the new vector. That's the meaning of this expression. And this unit vector is basically taken by the angle what is formed between the present reference frame alpha s beta s and the new reference frame alpha r beta r in counterclockwise direction. Do you get this understanding? I will write the equation again over here for clarity. What we have obtained IS referred to rotor reference frame from IS vector which was originally in the alpha s beta s reference frame by multiplying this unit vector e raised to the power minus j epsilon. So this is the general way if you want to shift your vector from one reference frame to another reference frame. You only need to multiply a unit vector which is given by the angle formed between the present reference frame and the next reference frame or new reference frame. And the angle must be taken in counterclockwise direction. So you need not solve for the components every time. You can simply take this as the rule. Now, if you know ISR, somehow you know this vector, and you want to write IS, what will you write?
Sir, E multiply by EJ epsilon.
Correct. So the reverse thing, if we know this vector somehow, if we know, and we are trying to compute this vector, we only need to multiply by the unit vector which is formed in the counterclockwise direction, the angle which is formed in the counterclockwise direction. Now this reference frame is known, alpha r, beta r. You are trying to jump back to alpha s, beta s. So angle is minus epsilon in the counterclockwise direction, which is why this becomes e raised to power j epsilon. You understand the point? If you are going in counterclockwise direction, you will have e raised to power minus j epsilon. If you are going in the clockwise direction, you will have this. It's the same thing. You just multiply the unit vector is power j epsilon on both the sides, it becomes this. But from the understanding point of view, I am saying. So when we are jumping between different reference frames and we have the vector to be computed in other reference frame, this is the rule which you have to remember. This is the simple rule what we must remember. Fine. Now we know the vector IR. Let's say IR is here. So IR is expressed in which reference frame?
Rotor reference.
Rotor reference.
Yes, in its native reference frame, which is rotor reference frame. So if I have to express IR in stator reference frame, what I will write?
IR e to the power plus j epsilon.
Yes, because we know IR vector in the alpha R beta R reference frame, and we are jumping back to alpha S and beta S, which is minus epsilon angle away in the counterclockwise direction. So now we have the understanding that how to compute the vectors in different reference frame. So we can plug in this in our equation which we have got earlier. These equations. You understand my point? So what I will write? Now I will write my voltage equation as Vs, IsRs, Ls, ddt of Is plus Lm ddt of IR multiplied by J epsilon. Now everything in this equation is known. We can measure IR, we can measure IS, we can measure Vs, we can measure epsilon, the angle. So epsilon, again I am saying that d epsilon by dt, or rate of change of this angle, is basically omega r, at which the rotor is rotating. Similarly, you can write the rotor equation as IR RR plus LR ddt of IR plus Lm ddt of Is e raised to the power minus j epsilon. So when Is is referred in rotor, it's coming as minus j epsilon. Understand the point? It is necessary to clearly understand how the angles are computed. Always we take counterclockwise direction as the positive angle. That is the thumb rule. We would not deviate from that. Do you understand this point?
Yes, sir.
Yes, sir.
Yes, sir. Yes.
Ashish, is that audible to you?
Yes, sir.
Okay, you may keep your camera off if network problem is there. So this is what we have obtained as the general equation for any, let's say, multi-phase machine, we can say. Because vector we are representing, we are not saying that it's only applicable for 3-phase. You can have 5-phase system also. So accordingly, your all the phases will be distributed in space and you can compute the vector. Particularly when you talk about 3-phase machine, yes, RYB you can express as a vector, voltage vector, and you are giving this equation. Now, from here, we can move for the special cases. What are the special cases? Let us say, for this symmetrical machine, what we have written over here, this could be applicable to, as it is, it could be applicable to wound rotor induction motor or doubly fed induction motor, same machine. So there what we will have excitation on the stator as well as rotor side. We will have current on the stator as well as rotor side. So then we need to use all 4 equations, 4 because you are having real and imaginary components over here. So all 4 equations we will have to take and solve. Now for something like squirrel cage induction motor, what we will have? We will have VR equal to 0. But still IR will be there. It's not equal to 0. Understanding my point? Now machine something like PMSL, we don't have rotor equation at all because there is no circuit on the rotor side. It's all magnet. So our rotor equation is not applicable. We have only stator equation to deal with the complete machine. But the question comes that when we are going for PMSM, say that rotor equation is not applicable. So which means what we have only one equation in terms of vector quantities. We have only one equation to deal with, and which is basically this. Now natural question comes, if there is no circuit on the rotor, what is this IR?
0.
Sir,
Don't jump on the conclusion.
it's like equivalent of flux. We
Yes.
represent as.
This is what we need to do. See what we have basically. We have magnets all over the rotor. Right? Which means what? So this is arranged like north, south, north, south, north, south like that. Now this means what? This is having continuous flux formed from this system. 3-phase we can somehow make number of poles and all these arrangements and we can find 3 groups RYB. Somehow we can do that. Ultimately what we are doing, we are dealing with a magnet over here. Now the question comes, how to model a magnet? This is something physical quantity. How do you model this in circuit? How do you write equation for this? So what magnet is doing basically, magnet is somehow providing us flux which is constant. It is giving us constant flux. It's continuously having these flux lines going in and out from the magnet. So the direction of flux lines is from north to south, right?
Yes, sir. Yes, sir.
What about inside the magnet?
South to north.
South to north.
Good, very good. That is why it forms a closed contour that must be there. So this is what we are trying to represent in terms of electrical system. So which means what we are trying to do, we are trying to have a system where we can have flux which is going continuously, which is constant flux. This is not varying, this is not AC flux, this is DC flux, which is there as it is. So what we can do, let us take a coil and somehow you initiate a current. Let's say, or I take a current source. This itself means it's a current source when coil is there. But let us just have some small element which is maintaining a constant current I. Okay. What will be the impact of this? How would it look like? Let's say you take a solenoid and just somehow maintain some current in that, constant current in that. So this will also behave like magnet, where flux lines will be going in this manner, similar to magnet. Do you understand this point?
Yes, sir.
Yes, sir.
Okay. So as of now, what we can do when we have PMSM to deal with, we can take some current. Okay, let us say IF current, field current is there. And this is having inductance L, which is basically magnetizing inductance. So that will come naturally in the equation. But the current we take as IF, say the field current. Now we don't have just one magnet sitting over there. We have multiple magnets. And ultimately it is somehow forming a three-phase system for the flux also. So what we should have set of coils which are distributed, say and we should have current associated with that. Let's say this is IF current. Now if this is IF current, we also have to ensure that KCL is also maintained. There is no source inside here. So whatever current is going in this direction must be coming from other phases. Total sum has to be 0 because we are dealing with balanced system. And then you close the circuit. Understand my point?
Yes.
This is your basically, you can say this is along the R axis, this is aligned along the Y axis, this is aligned along the B axis. Correct? So this is how we can form our system. Or let's say Y is here and B is here to maintain similar to our stator thing. So this is the arrangement how we can model the magnets on the rotor of the PMSM. Now if this is the arrangement, this is the current, let us say IF is the current. We have assumed, we don't know the value, but we have taken some equivalent number and we will try to compute what could be there. So then, similar to how we have been writing our vector in terms of IR, IY, IB components, we will write the vector for this arrangement also. So how that would come? IR, or to say IRR plus IRY e raised to power j 2 pi by 3 plus IRB e raised to power j 4 pi by 3. Now these numbers are not AC. No, IRR, IRY, IRB, these are not AC. These are constant numbers, IF. Then here you have minus IF by 2. And here again you have minus IF by 2. So what you have ultimately when you segregate this and solve, what you will see that the imaginary components will cancel out and ultimately you will have only 3 by 2 times of IF. Which means this vector has only real component available. The imaginary component is not there. Or in other words, to say that the way we have arranged this is alpha R axis, right? We know this is beta R axis, we know. So obviously the components along the beta are getting cancelled and everything is coming along the alpha R axis. That's the meaning of what you are getting over here. Fine. For simplicity, you can arrange it any other manner also. You can take IF along the Y axis and so you will have real and imaginary both components, but it will only increase your complexity, you know, when you put it in the equation. So this is what we are getting over here. Understand my point?
Yes,
any
sir.
confusion in this? Any problem?
No, sir.
Now we can replace this into our equation, the voltage equation what we have got. So we have got the number for IR or expression for IR although that's not measured, but we will somehow correlate with the magnet property. Now what we have is plus IF, and there is unit vector which is multiplied over here. Fine. This is not vector. 3 by 2 IF is simply a scalar number. Now you expand this or just simplify this, then what we will obtain Vs vector so 3 by 2 IF times of Lm, this will come out, and the differentiation of e raised to power j epsilon would be j times of d epsilon by dt times of e raised to power j epsilon. We know what is this d epsilon by dt. What is that?
Omega.
Omega. And we know that we are dealing with the synchronous machine, PMSM machine. So omega r is basically nothing but omega s.
Yes.
Correct. So I can write that j, and then here I can write 3 by 2 Lm times of IF times of omega s, let us say, and then the unit vector j epsilon. You understand this point? Now this is what is the property which is defined by the magnet. You can say this is some constant Ke, because it's all combined. This Lm is also from the magnet side, what flux linkage and for what magnetizing these things it is forming. Then IF is something what is part of the magnet. So this is something constant which is basically dependent on the magnet, and we can simply take as this. So if you have number of poles, that will somehow get adjusted in this. Now this I can write as j Ke omega s e raised to power j epsilon. Now, do you see some similarity with your DC motor? What is back EMF in DC motor?
Acha,
K5 omega.
Some K times of omega, right?
Yes, sir.
And this is DC motor. We are dealing with DC back EMF. Similar thing do you observe over here as well? This is the magnitude of your back EMF, but this is AC. So which is what this unit vector will give you, cos epsilon plus j sin epsilon. Epsilon can be expressed in terms of omega t. So that gives you AC back EMF. And this is the model of PMSM in stationary reference frame, alpha beta. So for clarity, this is not vector, right? This is simply scalar quantity Ke omega s. This is the unit vector multiplied here. We have vectors Vs and Is over here. So you can expand alpha beta components or RYB components, whatever you want. And then from the property of the magnet, we can compute what is Ke. What they will give that at rated omega s. What is the value of back EMF magnitude? This is what is generally given for any PMSM. So from here we can compute that what is the magnitude of EB, which means what is value of Ke times of omega s. So Ke simply can be computed from the machine ratings, omega s and EB and all. Correct? So all the things are known in this equation, right? Say something, yes or no?
Yes, sir.
Yes, sir.
Any confusion here?
No, sir.
Sir, last point not clear, sir.
What is last point?
EB equal to Ke omega s.
What is that EB into Ke omega? EB equals K into omega.
Sir, magnitude of above
Back
equation.
EMF, right?
Yes, sir.
So if you read data sheet of any PMSM, what they will say that if you rotate the motor without giving any stator excitation, if you rotate the motor at particular speed, you will find a particular magnitude of voltage. So which means they are somehow giving information about Ke. That's what I'm trying to say.
Yes.
Okay, so we can compute all the things in this equation, and then we can say that we have modeled our motor in stationary reference. So I stop here today, and next class we will start and move towards the control of this. Fine?
Yes, sir.
Yes, sir.
All right, everyone?
Yes, sir.
Yes, sir. Yes.
Yes, sir.
Okay.
Sir,
Yeah.
sir, like,
Hmm.
no, sir, not a doubt.
Okay.
You can end the